North Atlantic, February 1942. A British destroyer holds contact on a submerged U-boat. Sonar pings echo through the hull. The crew has done this 100 times. They know the drill. They know the odds. The odds are terrible. Depth charges roll off the stern in a spreading pattern. Barrels of amatol, time to sink and explode at a set depth. The sea erupts in white columns. The ship shudders. Everyone on deck holds their breath. Below, the U-boat commander does something almost insultingly simple. He waits for the exact moment the destroyer passes directly overhead, the moment its sonar operator, by the geometry of the attack, loses contact. And he turns. Just a turn, nothing more. By the time the charges detonate, he's 50 meters from where the Royal Navy thinks he is. He surfaces that night, undamaged, and radios keel. This will happen, in one form or another, thousands of times across the Battle of the Atlantic. Historians estimate that fewer than 1 in 20 depth charge attacks in this period actually sink their target, a figure that should be treated as an order of magnitude estimate rather than an exact one, but the direction is not in dispute. The weapon that was supposed to be killing U-boats was, for the most part, just making noise. Britain is losing the Battle of the Atlantic to a design flaw nobody in the Admiralty wants to admit exists. What none of these sailors know, what almost no one in the Royal Navy knows in February of 1942, is that 400 miles away, in a requisition building in London, a chemistry professor with no formal weapons training has just finished sketching an idea on the back of an envelope that will end this exact tactic, permanently. He is not a naval officer by trade. He has never designed a weapon in his life. He is about to build one anyway. To understand why this mattered, you have to understand what Britain was actually losing. By early 1942, German U-boats are sinking Allied merchant shipping faster than British and American yards can replace it. Convoys are the lifeline: food, fuel, ammunition, the raw material of a war effort, and every ship that goes down is weeks of production, hundreds of tons of cargo, and often dozens of lives, gone in minutes. Winston Churchill will later write that the U-boat peril was the only thing that ever frightened him during the entire war. The Royal Navy's primary weapon against this threat is the depth charge, and the depth charge has a flaw baked into its very geometry. ASDIC, Britain's early sonar, can detect a submerged U-boat's bearing and range with reasonable accuracy. But as the attacking ship closes in for the kill, the angle changes. In the final seconds before the ship passes over the target, the exact moment the depth charges need to be dropped, the sonar beam passes over and past the submarine, and contact is lost. The attacker is, for those crucial seconds, blind. Any U-boat commander who understands this can exploit it. And by 1941, most of them do. Turn hard the instant contact breaks, and the depth charges detonate over empty water. The Admiralty knows about this weakness. It has known for years. The response, largely, has been more depth charges, bigger patterns, more charges per attack, faster reload systems, throwing more amatol at a problem that isn't really about quantity. Naval ordnance officers, when the idea of an entirely new weapon is raised in committee rooms through 1940 and 1941, tend to give some version of the same answer. Depth charges work, they've always worked, and a submerged target moving at speed in 3 dimensions is simply too difficult a problem for anything more precise. The consensus is not stupidity, it is caution, built on a weapon that has, after all, sunk U-boats before. Just not nearly often enough. The stakes could not be higher. Britain imports most of its food and nearly all of its oil. If the convoys stop arriving, the war is over. Not through invasion, but through starvation and immobility. Every percentage point shaved off the U-boat's survival odds is measured, quite literally, in whether Britain can keep fighting. What's needed is not a bigger depth charge. What's needed is a weapon that can be fired without losing contact. One that solves the geometry problem instead of trying to overpower it. Nobody inside the traditional naval ordnance establishment is building that weapon. Somebody outside it is about to. His name is Charles Frederick Goodeve. He is not, on paper, anyone's idea of a weapons designer. Canadian-born, trained as a chemist, he spent the interwar years as a university professor, research into chemical kinetics, not ballistics. When war breaks out, he's commissioned into the Royal Naval Volunteer Reserve, the wartime branch stocked with civilians rather than career officers, and assigned to a scrappy, semi-official unit with an almost self-deprecating name, the Department of Miscellaneous Weapons Development. Inside the Navy, the unit has a nickname, half affectionate and half dismissive, the Wheezers and Dodgers. It's where you send the odd ideas nobody else wants, the ones too strange, too underfunded, or too far outside doctrine to belong anywhere in the conventional chain of ordnance development. Goodeve fits right in. He has no formal training in mortars, fusing, or ballistic trajectories. What he has is a chemist's instinct for asking why a system fails at the molecular level, and a habit, unusual for the era, of listening to junior officers and enlisted sailors who complain that depth charging simply doesn't work often enough to justify the effort. The insight, when it comes, is almost embarrassingly simple in hindsight. If the problem is that the ship loses sonar contact the instant before the drop, because you have to be directly above the target to drop a depth charge, then the answer isn't a better depth charge. It's a weapon that doesn't need you to be above the target at all. A weapon fired forward, ahead of the ship, while sonar contact is still locked on. A weapon that only explodes on contact with a hull, not on a timer, not at a set depth, but only if it actually hits something. So a miss makes no noise, no white water, no warning. The U-boat wouldn't even know it had dodged anything, because nothing would have gone off to dodge. Goodeve sketches a pattern, a spread of small mortar bombs, fired in an ellipse ahead of the ship, dropping onto the water and sinking together toward wherever the sonar says the submarine is, all while the ship stays in contact the entire time. He doesn't yet have a name for it. He's about to build one in secret, with almost no budget and even less official support. DMWD's working space is about as far from a proper naval design bureau as it's possible to get. By some accounts, a repurposed corner of the Wembley Stadium complex, borrowed office and storage space pressed into wartime service. No test range, no dedicated ordnance engineers on staff, no budget line for a new weapons category, just Goodeve, a handful of like-minded oddballs, and whatever parts they can scavenge or fabricate. The mechanism they land on is called a spigot mortar, a stripped-down, almost primitive firing system. Instead of a conventional barrel, each bomb sits on a spike, or spigot. A propellant charge drives it off the spike and into the air. It's crude, it's cheap, it's fast to build, and critically, it lets you mount 24 of them in a single frame, fired in a timed sequence that scatters the bombs into a ring pattern on the water ahead of the ship. The prototype looks less like a naval weapon and more like a piece of agricultural machinery bolted to a foredeck. Rows of black canisters angled skyward, ugly and unmistakably improvised. The first test firing does not go well. Early trials produce erratic patterns, misfires, and at least one incident serious enough that officers watching from a safe distance visibly flinch. Contact fuses, the idea that the bomb only detonates if it physically strikes something, are themselves a point of alarm, because a contact-fused explosive sitting on deck, armed and ready, is a very different safety proposition than a depth charge with a timer nobody sets until it's already in the water. When word of the project reaches more conventional ordnance officers, the reaction is exactly what you'd expect from an establishment that has spent 2 decades refining depth charges. You want to put 24 live contact-fused bombs on the deck of a warship, fired forward in a spread, from a mechanism a chemistry professor designed in a stadium office. One senior officer, reviewing the concept on paper, reportedly calls it reckless, a fire hazard as much as a weapon, and not remotely ready for a warship's deck. In an era of strict ordnance certification, an untested contact fuse system built outside proper channels sits somewhere between irregular and against every safety regulation we have. Goodeve's answer is simple. It doesn't matter how strange the weapon looks. It matters whether it solves the geometry problem. Depth charges can't, and by his own early trials, it does. Now he just has to convince the people who can put it on a ship. Getting Hedgehog, the weapon now has its name, inspired by the bristling look of its mortar spikes. From prototype to production means surviving the Admiralty's committee process, and that process is where the project nearly dies. The core objection isn't really about performance, it's about culture. Depth charges are a known quantity, predictable, familiar, backed by 20 years of doctrine and training. Hedgehog asks captains to trust a system where a miss produces nothing. No explosion, no confirmation, no satisfying column of water telling the crew they did something. To a service that measures success partly by visible aggression, a weapon that's silent when it fails to hit feels, to some officers, like it isn't doing anything at all. At one pivotal demonstration and review, accounts describe a room of ordnance officers, several openly hostile to the entire WWII program. The argument turns heated fast. Objections stack on top of each other. The contact fuse is too dangerous to arm and stow at sea. The 24 bomb pattern is unproven against a maneuvering target. The whole concept diverts scarce wartime manufacturing capacity away from a depth charge system that, whatever its flaws, is at least understood. The room erupts. Voices rise over each other. Someone reportedly calls the entire project a dangerous distraction dressed up as innovation. Exactly the kind of clever thinking that gets sailors killed by their own equipment rather than the enemy's. Goodeve holds his position on the numbers. Depth charges are sinking a small fraction of the U-boats they attack. Even by the Navy's own optimistic internal estimates, the kill rate is grim. Hedgehog, in trials, is already showing it can maintain sonar contact through the entire attack run, something no depth charge pattern has ever been able to do. If the pattern holds in combat, even a modest per-attack kill rate would represent a dramatic improvement over what depth charges have managed for 2 years of war. What tips the balance isn't a technical argument. It's that dude, and Goodeve specifically, has cultivated a reputation, including by several accounts, direct interest and support from Winston Churchill himself, who took a personal fascination with the unconventional weapons programs coming out of units like Dude throughout the war. Whether or not Churchill personally intervened in this specific decision is a detail worth double-checking before it's stated as fact on screen. But what's well established is that WWII's odd, high-risk projects had backers at the very top of the wartime government willing to override a skeptical ordnance bureaucracy when the underlying math was sound. That backing is enough. Over the strenuous objections of parts of the ordnance establishment, Hedgehog is approved for shipboard trials and limited production in 1942. It is, by any normal peacetime standard, a strange way to greenlight a weapon, not through the ordinary chain of naval design authority, but through a chemistry professor's math and a willingness, somewhere well above committee level, to bet on an outsider's idea. The first units go to sea within months. If a story like this, the outsider nobody trusted, solving a problem the professionals had accepted as unsolvable, is the kind of history you want more of, hit subscribe. By 1943, Hedgehog is fitted across a growing number of escort ships, and the numbers begin to tell their own story. Early Royal Navy assessments comparing Hedgehog attacks against depth charge attacks over the same period show a meaningful jump in kill rate per engagement, commonly cited at somewhere in the range of 2 to 3 times the depth charge's success rate, though the exact figures vary by source and by year, and should be checked against Admiralty ASW analysis records before being quoted as precise statistics on screen. The core reason is the one Goodeve identified from the start. Hedgehog doesn't force the attacking ship to fly blind in the final seconds of the run. Sonar contact holds all the way to impact. Picture the moment. An escort holds a submerged U-boat on sonar, closing the range. There's no need to pass overhead and lose the picture. The mortar frame fires forward, 24 bombs arcing out in a ring ahead of the ship's bow, dropping together toward the target's last known position. The crew doesn't hear the satisfying roar of a depth charge pattern. They hear almost nothing. Then, underwater, a hull ruptures. For the U-boat crew below, the tactic that has kept them alive for 2 years, wait for the blind spot, turn hard, vanish, simply doesn't apply anymore. There is no blind spot to wait for. The attack that sinks them arrives from directly ahead, while the escort is still tracking them perfectly. A composite of post-war U-boat commander accounts, again dramatized rather than a single verified quote, captures the shock of it. We turned exactly as we had 100 times before. There was no reason to think this time was different. Then the hull gave way, and we understood nothing about this attack had followed the old pattern. For Allied sailors, the payoff isn't abstract. Every U-boat that Hedgehog takes off the board is a convoy that gets through, a cargo of food or fuel or ammunition that reaches Britain instead of the seabed. Veterans of the escort fleets, interviewed decades later, describe it in the simplest terms survivors tend to use. Because of a weapon nobody trusted at first, we came home, and so did the ships we were guarding. By the war's final 2 years, Hedgehog and its successors will be credited with a substantial share of the U-boat kills scored by British and American escort forces. A professor's forward-firing mortar, succeeding where 20 years of depth-charge doctrine had plateaued. There's a full playlist of stories like this. Weapons, tactics, and people the history books tend to skip past. Visit the playlist if you want to keep going after this one. Hedgehog didn't stay a wartime curiosity. It was adopted, refined, and exported. The U.S. Navy fitted it across large numbers of its own escort ships, and post-war navies developed direct descendants, including the British Squid and Limbo systems, which extended the same core principle, forward-firing, contact-fused, contact-maintained, for another generation of anti-submarine warfare. Variants and philosophical descendants of the forward-throwing ahead mortar concept remained in service with several navies well into the Cold War, and the basic tactical insight, don't sacrifice sensor contact to make the kill, still underpins modern anti-submarine weapon design. Charles Goodeve did not spend the rest of his life telling this story. By most accounts of his post-war career, he returned to scientific and industrial work, and when Hedgehog came up, he tended to redirect credit toward the wider DMW team, the machinists, the ordnance testers, the Wheezers and Dodgers who built and rebuilt the prototype through 1941 and 1942, rather than positioning himself as the singular inventor. It's a posture that shows up again and again in accounts of the unit. People who solved an enormous problem and then treated it as a group effort rather than a personal legacy. The lesson underneath all of it isn't really about mortars or sonar geometry. It's about where solutions come from. The Royal Navy's ordnance establishment had 2 decades of expertise, real operational experience, and no shortage of intelligent people working the depth charge problem. What it didn't have, until DM'd, was someone willing to ask whether the entire premise of the weapon, attack from directly above, lose contact right when it mattered most, was the actual flaw. It took an outsider, one without the credentials the room expected, to see it. The U-boats that turned into what they thought was a blind spot and found nothing waiting there anymore never got the chance to learn who Charles Goodeve was. They just stopped coming home.